time steps in the loading history. The ExVis program is still being developed to examine the response that is measured using the Krypton camera. We are currently working on calculating the distribution of vertical straining between vertically adjacent LEDs. There are many other capabilities that are still being explored, including how to fuse data from different measurement sources to obtain the best possible estimate of the state of strain and stress in the structure at all points with quantifiable accuracies. The development of the ExVis program provides justification for collecting dense experimental test data. The ExVis program also provides a powerful educational tool that goes well beyond simple test videos, as ExVis enables one to quantitatively explore the measurable response of test structures. The system architecture for ExVis was developed to be quite general so that it could be readily expanded to other applications. It adopts a relational database technique to manage the measured data and uses two-way linked lists to store all structure and instrument information. This system was implemented using an object-oriented approach. The crack locations that were shown in the demonstration were obtained from high-resolution photographs using principles of close-range digital photogrammetry. By using reference coordinate information contained within each photograph, it was possible to transform the position of each crack from image coordinates to girder coordinates to an accuracy of about 1/8 of an inch of the measured location of the crack. As demonstrated, ExVis can be used to combine the data from multiple measurement sources with full geometry and material property information to more fully characterize and understand the response of test structures. Expanding upon the example shown in the demonstration, ExVis was used to draw a free body diagram for each of 350 diagonal cracks, and from this it was possible to develop general relationships to characterize what portion of the total shear force would be carried by transverse reinforcement, Vs, and concrete, Vc, throughout the loading history as a function of the concrete tensile strength, the amount and strength of the provided shear reinforcement, and the relative stiffness of the uncracked concrete and transverse reinforcement. The dense measurement data in ExVis program also made it possible to understand and characterize numerically many other aspects of the response of the girders, including demands on longitudinal tension reinforcement, shear stiffness characteristics, and the angle, spacing, and width of all cracks. Advanced measurement systems and image analysis techniques can be used to provide very dense and accurate information about the response of test structures. Similar to the Krypton measurement system, as shown in the top of this slide, close-range photogrammetric methods can be used to obtain the coordinates of hundreds or thousands of points on a test structure to an in-plane accuracy of a few 10,000ths of an inch. The cost of the equipment for this latter system is only about $10,000. The capabilities of these systems help define the needs and possibilities for data visualization tools such as the ExVis program. With the density of test data approaching what can be predicted from numerical analysis models, coupled with advanced experimental data visualization and analysis methods, it is now possible to better imagine and develop the model validation frameworks that are needed for assessing and improving the capabilities of nonlinear computational tools. Through these comprehensive assessments, it will be possible to evaluate the reliability of computational tools for predicting many aspects of a structure's performance, and thus to use these tools in the design of structures to meet specific performance objectives and for making more meaningful assessments of existing structures. Two examples are now used to illustrate some of the model validation possibilities. This slide presents a comparison between the predicted and measured state of cracking in one of the test girders. Possible validation metrics would include comparing quantitatively the region, angle, spacing, and widths of all cracking over the entire loading history of the structure. Another important model validation activity is assessing the ability of a computational tool to predict the mode of failure. The figure on the left presents the ratio of the compressive stress to compressive stress capacity in each finite element. This figure illustrates that the mode of failure was predicted to be by crushing of the web, as shown in green, in the region where the diagonal compression funnels to the support at the right end of this girder. This is consistent with that observed in the experiment as shown in the photograph. This photograph also illustrates the complexity of the observed cracking, spalling, and crushing, and thereby several challenges. 1. For making the measurements that are needed for characterizing experimental response. 2. For the numerical modeling of complex and localized behavior. 3. for the development of data visualization tools for presenting the measured response, and 4, for establishing comprehensive model validation procedures and metrics. The advancements in measurement and data visualization tools that were presented in this video help define the potential for properly designed experimental research programs to develop, calibrate, and validate computer-based numerical models. This role is consistent with that envisioned in the National Science Foundation Needs Program as presented in the description of this collaboratory. Your comments and input on the ExVis program are welcomed at kuchma@uiuc.edu. Additional information on developments in ExVis capabilities and model validation frameworks will be updated at dankuchma.com. Thank you for your time in viewing this presentation. Goodbye.